Hello everyone. I am going to explain about instrumentation amplifier, clipper, clamper in this video lecture using op-amp. I am going to discuss the applications of op-amp, instrumentation amplifier, the design using three op-amp and its application, and we are going to derive the gain of the amplifier. Then followed by clipper and clamper and the positive and negative configuration using op-amp. An instrumentation amplifier is a high precision differential amplifier which is designed to amplify very weak signals while rejecting the noise common to both inputs. Hence, it has high CMRR, which is common mode rejection ratio, and has high input impedance and low output impedance. It is a critical component for sensors like thermocouples, strain gauges, and medical equipment in real-time applications. Thus, it is used for small signal amplification. The architecture of the op-amp is given using three op-amp, which is split into two stages. In first stage, input buffers will design using two op-amps, which consist of two non-inverting amplifiers and they act as buffer. Then next is the differential amplifier stage, and it is act as a voltage subtractor, and the gain is controlled by a single resistor which is connected across the two input buffer amplifiers. The circuit is designed using three op-amp, which is shown in the circuit diagram A1, A2, A3. It has the first two stages are A1 and A2, which are two input buffer amplifiers, and the stage 2 consists of single amplifier, one differential amplifier stage. It performs the subtraction, and the gain is calculated from the output of the third amplifier A3. The gain is given as 1 plus 2R1 by Rg, which is connected across the two amplifiers A1 and A2 into R3 by R2. The gain adjustable by varying Rg, and it is high accuracy and stability is maintained in this instrumentation amplifier. Certain applications of instrumentation amplifier are mainly in biomedical instrumentation, in ECG and EEG, and it is also used in strain detection, and industry process control. In practical application, an instrumentation amplifier is almost always used in tandem with Wheatstone bridge as shown in the circuit diagram. It is connected at the input of the op-amp. It is used to convert the physical changes like pressure, temperature, or strain into measurable voltage. Most sensors like strain gauges, RTDs, and pressure sensors are resistive. To measure the small change in the resistance, they are placed in the bridge circuit. The DC supply voltage always powers the bridge. The physical quantity is at its base state. The bridge is balanced, that is V1 is equal to V2, and the differential output is 0 volt. Hence, the tiny millivolt from the bridge is fed directly into the high impedance input of the 3 op-amp instrumentation amplifier. The first two op-amps provide nearly infinite input impedance, ensuring the bridge circuit is not loaded down, which would cause measurement errors. Transducers often use long wires that picks up 50 to 60 Hz hum. The in op-amp's high common mode rejection ratio cancels this noise because it appears equally on both wires. We can scale the bridge millivolt signal to a 0 to 5 volt range suitable for the embedded system interface using Arduino or PLC by adjusting the single resistor RG. Thus, it is employed in instrumentation systems. An op-amp clipper is also called precision clipper or active clipper. It is a circuit which is used to limit or cut off a portion of the input signal that exceeds specific reference voltage which is given in the another input terminal of the op-amp. It removes the unwanted portion of the signal. The two main configurations of clipper are positive negative clipper. It is based on the polarity of the reference voltage given at the input terminal. The clipper circuit uses diode along with the op-amp. Unlike passive diode clippers, which lose about 0.7 volt due to diode forward voltage drop, op-amp clippers uses high gain to compensate for this drop, creating an almost ideal clipping action. The circuit diagram is shown in this, in which op-amp along with the diode is act as the positive clipper. Here the input signal is given to non-inverting terminal and the feedback portion of the output voltage is connected back to the inverting terminal. Thus, it acts in the mode voltage follower. The reference voltage is given to the positive supply. Thus, the circuit acts as the positive clipper. When you see the waveform, the input is a sine wave and your V reference, if it is positive, then when the portion above the V reference voltage will act as the voltage follower. Hence, the output voltage follows the input above the reference level. Below the reference level, the output voltage is 0. And similarly, if V reference is negative, accordingly, the portion below the reference level is clipped off and portion above the reference level as voltage follower, thus output follows the input. The waveforms are thus shown in positive clipping and negative clipping. The clipper circuit is classified as positive clipper and negative clipper. It clips the positive portion above the reference level in the positive clipper. When Vin in a typical non-inverting configuration, when Vin is less than the V reference voltage, the op-amp output is driven toward positive saturation, forward biasing the diode in the feedback path. The circuit will act as the voltage follower and the output V out exactly matches the input V in. When V in is greater than V reference, the op-amp output is reversed and hence it reverse bias the diode, breaking the feedback loop. The op-amp enters an open loop state and the output is held constant equal to the reference voltage V reference. Thus, in the positive clipper, it clips the positive portion of the signal. Here in the negative, the V reference is connected to the negative power supply and is perform the vice versa operation of the positive clipper. It clips the negative portion below the reference level and diode variation is reversed. Thus, the positive clipper acts fully. An op-amp clapper is a circuit used to add specific DC offset to an AC signal, effectively shifting the entire waveform up or down without changing its shape. Unlike the passive diode clampers, the op-amp version eliminates the standard 0.7 volt drop, which makes it suitable for low voltage precision signals. The types of op-amp clampers are mainly positive and negative clamper. Positive clamper shifts the entire waveform vertically upward. The negative peaks of the signal are clamped to a specific reference level. Negative clamper means it shifts the waveform vertically downward. The positive peaks are clamped to the reference level. So the precision clamper typically uses an op-amp, a diode, a capacitor and a resistor. During the charging phase, in one half cycle, the op-amp drives the diode into conduction, allowing the capacitor to charge quickly to the peak value of the input signal. In the clamping phase, during the next half cycle, the diode becomes reverse biased and the capacitor, which cannot discharge quickly due to high value load resistor, will act as a DC battery in series with the input. Hence the output is Vin plus Vc, which is the capacitor voltage, resulting in shifted waveform. Practical applications of clamper are DC restoration, voltage amplifiers, analog to digital interfacing. In DC restoration, it is used in video systems like TV to restore the DC baseline of the signal. In voltage multipliers, it acts as a building block for voltage divider and tripler circuit. In analog to digital interfacing, it shifts the bipolar signal into strictly positive range for microcontroller ADCs. Thank you.